This is how we built a quadcopter drone completely from scratch, explained in less than 4 minutes. Started out by testing a few motors and then mounted them on this 3D printed arm so that we could start experimenting with controlling angles. Once that was done, we designed this body and on shape, which we 3D printed, and after that we assembled everything. And don't ask me why this was done in my kitchen. With everything assembled, we could now start designing a flight controller. A controller is basically something that adjusts the input to a system to make the output match a desired target. In our case, we used a PID controller, which consists of a proportional, integral, and derivative part, where each part has their own tuning coefficient that can be varied to make the system behave differently. In order to obtain good tuning coefficients, we performed an experimental analysis of system behavior for different values. With the controller implemented, we then performed a few flight tests. This was first done in a wired configuration, and once we were happy with the performance, we started on working on making the drone wireless. For this, we needed a good remote. We therefore designed a custom PCB in KiCad, which we ordered from PCBWay. The remote and drone both use the same ESP32 microcontroller, which has integrated wireless capabilities, meaning we did not need any external antennas or receivers. Here is one of the tests we performed with the drone completely wireless. As you can see, it kind of works, but still not super well. This was mainly due to the fact that we used a rather simple flight controller, which was only able to control the angular velocity of the drone. We therefore set out to design a more advanced flight controller, which can also control the angle of the drone. The controller we chose is a cascaded PID controller. This means that it consists of two PID controllers connected in series, where we have an inner loop with a fast response that can handle most of the stabilization tasks, as well as an outer loop with a slow response that can make sure any remaining errors are eliminated. The outer control loop also uses a Kalman filter as observer. The Kalman filter is a signal processing algorithm which combines the measurements from the gyroscope and accelerometer to get a better estimate of the drone angles than would have been otherwise possible. With the new flight controller in place, we then performed new flight tests, and as you can see, the performance is now way better than with the old flight controller. However, the drone still crashes. After doing some troubleshooting, we were able to conclude that the drone was too heavy and that the DIY battery we had built was not able to supply enough current. We therefore replaced the battery with this one that is specifically designed for drones and made mechanical optimizations to the frame of the drone to make it lighter. After this was done, the drone seemed to work really well and we were very happy with the results. If you're interested in building your own drone, you can find all the files for our project on GitHub, and we also want to give credit to Carbon Aeronautics, whose GitHub we have been using quite a lot during our project. Thank you for watching our video.